Okay, so I would like today to solve some, not everything. It's impossible, like in a few minutes, but some like exercises, and I want to start with some joins and meets because we haven't solved any exercise like together, and this is quite important to see like how we can attack these kind of things, and we'll find out that this is not so new after all. So it's been a homework for a while that to show that every lattice is it's not necessarily fully distributive or fully modular, but it's like halfway there. And the idea for this is like that satisfies what I call the safe distributivity law and the safe modularity law. So the safe distributivity law is something like that. You have B joined with A meet B. Now the distributivity law would be that this is equal to, okay, so actually there are two distributivity laws because we have two binary operations and one may distribute over the other. So the way I have started this is like that join distributes over meets. So this would be that this is equal to D join A help me here, like meet D join B. So this will be the distributivity law, and I have there's another homework that asks you to find a lattice that does not satisfy this law. So what is the safe distributivity law? It's one direction only, and it's the one that says that actually the join, so this is a join, and this is a meet. So it says that the join is less than equal to the meet. It might seem counterintuitive, but this holds in any lattice. Okay, so let's say I want to prove this. So I will not call this. This will be like the safe. Okay. The idea that we should figure a way to name all those theorems and all those laws in a consistent manner. I'm pretty sure they have not been very consistent in my notes, but okay. So ideas, how do I go around proving this? I only know that's a lattice. Oh, okay, sorry. And there's another, obviously, distributive law that says that meets distribute over joins. Technically, the laws that I have written down, they say that it distributes from the left. But I do not need to worry about this. Why? Someone? Yes? No, this is not duality. Wait. So, I think you are answering a different question. And if you are, do not repeat this answer in the next question. So this is a hint. So let's see what I mean. So the first question is, what would be this is distributivity, forget this one. Okay, this is distributivity of joins over meets from the left. Why? Because I'm joining from the left. Right? So I'm saying that it should be pretty obvious that I don't need to worry about, let's say I prove this, joining from the right, which would be something like that, swapping this. Why do I not need to worry about this? Yes? The commutativity. Both of these things are commutative, so like if I have this, I can just flip these two because join is commutative, and this join is commutative, and this join is commutative, so I will never worry inside the lattice, or even in a semi-lattice, about the order of that I'm operating. Joins and meets are always commutative in what we're doing. So this is why I don't care about to specify like a left or a right, but technically this one that I have written here is from the left. Okay. So what is the second law I have written here? It's also from the left, but what changes? Oops. But what changes is that I'm now distributing not joins over midts, but midts over joins. And now comes my second question, and remember the hint. Let's say I have proven this. Do I need to worry about this? So if you remember the hint I gave like 2 minutes ago to ERRATA, you will not say what you might be tempted to say. So what is tempting to say here, obviously? You can say it again, or was it? The duality thing. It might be like, it's easy to get fooled here, like carried away, and think that, okay, if I prove this, I will not need to prove the other one thanks to duality. Kinda yes and no. I want to see what exactly I can get from duality and what I cannot, because it's an easy way to confuse yourself. Yes, Lazarus?
If we flip the lattice upside down, essentially the middle joins reverse.
So this would be like the duality thing. You're saying that joins and midts are reverse. So if you prove that in any, let's say if you prove this, right? You should get for free this thing, maybe. But what's the catch? If you flip your thing upside down, the joins become midts, the midts become joins, but also this becomes this, right? So if you want to have an equality here, you cannot get it exactly for free of one from the other. You will need to prove this. Does that make sense? Okay, so be careful there with what exactly is the dual one and what you gain. You have a duality principle for lattices, but you will not get this one out of this one like that for free. Okay, so let's say, okay, enough with the warnings. Let's try to prove this. Okay, cannot see well here, but yeah, this slide is annoying. Okay, so ideas. I have D, join, I will copy it. Any ideas, or should I just start giving hints? Okay, fresh blood enters the classroom, so maybe we have, we're looking for ideas of how we could prove this. Okay, so one way to do this is like visualize, I have like here a join and a mitt. And I could visualize this as like something like that. I do not want to mess with the colors I've chosen, but anyway, I might mess it. So this is one thing, let's call it a red thing, and I want to show that it's less than or equal to the join of two other things, so let's call them the green and the blue. And now the question is, how can I prove that something, the red thing, is less than the the mitt of two things? I think I said join. Now you may see it or not. So the thing on the right is the mitt of two things, which means it's the biggest lower bound. I'm emphasizing the shape of this thing because like it's this lower bound and everything is below it. So if you want to show that something is below this thing, it's enough to show that it's below, it's somewhere here, right? Can you see these things I'm doing? Yes, okay. So the idea is that you can reduce it, yes, Arati? Okay, you are way ahead of us right now. We will go there. So I'm happy with this comment by Arati. So the idea is that In order to show that a red thing is less than or equal to join, I have to show it's sufficient to show that it's a lower bound. Because the other thing is the greatest lower bound, so if it's a lower bound, it's less than or equal than the greatest lower bound. So here I would do something like, okay, I will not repeat all those things. I will repeat the red one actually. I have to show that this thing is less than or equal to something, and also to the green, and also to the blue. Okay, I might carry it with me actually. Okay. Does that make sense? Yes, okay. So what do I do now? Sorry. Now, if I look at this green thing as an atomic thing, like I did down here, it doesn't really help me because I want to show that something is less than or equal to a join. But the join is not the greatest thing of something, it's the least thing of something, so this will not help me. But I want to show that this thing is greater than a join, so it's sufficient to show that this thing is somewhere here. Does that make sense? So okay, yes, it's a question or an answer? Okay, so what should I do here?
Θέλουμε από πάνω να έχουμε το τι μικρότερο join A.
Yes, okay, so you want that this thing is less than or equal to the join A. And this, that's what you're saying, right? Does that make sense? So every time I'm reducing something, and I started here by looking at this thing as I want to show that something is less than or equal than a meet, ignoring the fact that the left-hand side was a join. What would be an alternative here? Yes?
We could have started on the left.
Which means, how would this thing look like? I mean, okay, let me copy this. Okay, first the things are, the colors now are completely wrong from what I'm trying to do. So here the coloring would be like, consider this like, this to be something of like an atomic thing. And now you see this as something, and this as something. So you want to show that the red is greater than the join of the green and the blue. So here it would be like what? Okay. So this would be like D is less than or equal to the red thing. And on the other hand, that D is less than or equal to the blue thing. And now you will look again. So ERRATA already noticed that this is extremely similar to what we were doing. Like we've seen it like 3 or 4 different incarnations of it. Like, will I ask help from the product first and then from the co-product, or will I try to split my goal and then separate in cases, or like the other way around? So, and so on and so forth. Actually, here, it's not exactly so on and so forth, because soon we will hit a wall. Maybe we have hit a wall already. Yes, I can carry this a little bit further. So can somebody help me here? Now the colors are, once you do the colors like below, you should forget about them, because you need to recolor in a different way. Okay, some help here. What do I do here? Yes, ERRATA? So, sorry, but before you get to answer this, let me know, are you like focusing on this thing or on that thing? On the left-hand side, yes. The other one is useless in this way of thinking, right? Because I want to show that something is below the least upper bound. It doesn't help me. But this one is helpful because I want to show something is greater than that. Yeah, so what do I do? Great.
A and B. We brought it to D.
Okay, very well. So on the right hand side, can I get help from anything? I do have a join and I do have a meet. So which one will help me here? The join? Is that that one?
Όχι, θέλω να πω το αριστερό είναι σωστό έτσι κι αλλιώς.
Okay. Sorry, I'm not comparing. Okay, you're saying this and that. Okay, so actually, what ERRATA is saying is that we can show this, and somebody can doubt this, but I'm pretty confident that we can all see this. Okay, this is like, justify this, but I think it's kind of obvious. D is less than or equal to D join B. So technically we need a kind of theorem or something like that. Okay, let's do that now. Let's not do it. Okay, let's focus here. Let's focus on the left. I want a good reason. Why is this the case? Yes?
Είτε το ότι θα είναι μικρότερο του B, οπότε...
Ooh, I don't like the way you started. Be careful. It's the order is not total, right? Maybe I judged you too quickly. Okay, but okay. So as I said again, you want to show here that D is less than or equal to itself joined with something.
Ναι, ότι το άλλο something είτε θα είναι μικρότερο από το D,
Okay.
το join τους θα είναι από το D και πάνω, ήταν μεγαλύτερο από το D, το join τους εξορισμού θα είναι πάνω από το D.
I'm confused. I confess. Did anyone get what he said? I mean, can somebody help me get what he said? Okay, so it's not me. But but like, if you want to split in cases, like which of the which cases are you splitting here? It looks like you're saying either it's this case or it's that case. In both cases, I have what I want. So what are the two cases?
Το D μικρότερο του B και το B μικρότερο του D.
Okay, so my initial concern. These are the cases that you got.
No.
Okay, so this is in fact what I was like worried initially. It's not a total order. It's very common because we are used to say, okay, either A is less than or equal to B or B is less than or equal to A. It's not. We don't have that. It could be that it could very well be that they are incomparable like that. I mean, let's say that this is D and this is B. Neither D is less than or equal to B, nor B is less than or equal to D. Okay, but it's a very, very common thing to separate in case, so be very careful when you're solving exercise or proving things with orders. Unless you are in a total order, pretty much we will do nothing with total orders here. They're not so interesting for us. We will never be able to split in these cases. But there is a good justification for this. Yes, Sotiris?
D less than equal to D is sufficient.
You mean like that?
Yes.
How will you reduce this to that? Okay, so the things we have been using so far is like the bestness of the join. Remember, join has a property, it's what? It's an upper bound, and its bestness means what? That it's the lowest upper bound. And so far I have only used this. And about meets, I have only used the bestness of the meets. I have only used that it's the greatest than any greater bound. Now it's time to use the fact that the join is an upper bound, and there are two ways that this manifests itself. This is greater than D, and it's greater than B. So, after all, this is an upper bound of D and B, so which means that it's greater than D and it's greater than B. So it's half of one of the two things that it needs to do, and while here, it's the fact that it's the best that we're using. So here it's like the introductions rules. If I see this as proofs, I'm saying that D can prove D conjunction with anything, right? This is the introduction rule, while here it's the elimination rule. I say, I have this, how do I prove something? So here, this is like, I don't know how I should label this right now. This thing is an upper bound, and I'm using the leftness of this. There's another thing that says there's an upper bound of, it means that's greater than B. Okay, so let's focus. Is that okay? Are we fine with this? D join B is an upper bound of D, and it's also an upper bound of B. And of all those things that are common upper bounds, it's the best. I don't care about the best right now. Okay, so back here, like, should I check meet or should I check join? Which of the two seems to be helpful? Meet. Was it like a... Okay, so if I want to take advantage of the fact that on the left I have a meet is smaller than something,
I mean, you will need to use both.
Just a second. It's not like before, because before I wanted this, and if I have this, meet helps me because I just need to show that this is somewhere below this thing. But now I have, if you think that meet is going to be helpful here, I want to show that something is greater than the meet, but meet is already the greatest of all those things, so this is not going to help me. But for the same reason, the dual reason, this seems to be useless here. They are in the wrong side of this thing, if you want to see it that way. Joins were helpful on the left, if I have this. Okay, I say left and right, I'm thinking about this. Obviously, if you think about that, it's swapped. So since I'm here, meet here is useless, and join here is useless. Do we see that? It's the same thing as if like you were trying to remember to create an arrow, and you had a plus, and you want to go here. Now both of those guys can help you. You can choose to start on the left, on the right, both are helpful. The worst thing would be if it's like that, because you are going out of a product, and the product doesn't help you to go out, it helps you to get in, and you are getting inside a sum, and the sum doesn't help you to get inside, it helps you to go out, to define functions out of it, not into it, okay? So this is helpless, not helpful, not helpful, helpful, and helpful, right? Do we see that? Okay, so back here, I cannot ask for help from the join, I cannot ask for help from the meet. So like, do I give up, or is there any idea I could do? Yes?
I mean, the fact that we have these on both sides seems useful. I don't use it exactly, but...
Okay, that's a very good observation. So I have B here and B here. There's something connecting the two. It's not exactly like the best I could think of, but it's definitely not something to ignore. And this is something I haven't used so far, which is very helpful when you're dealing with lattices. It's the dual aspect that you have like algebra and you have order, and I haven't used any properties technically of this thing so far. So like maybe I used the reflexivity somewhere, I don't know, no. At some point, Sotiris suggested something that if it were to work, eventually it would be like that, right? And at this point, how would I get this? I would say, reflexivity of this order, okay? So reflexivity doesn't seem so helpful here. Yes?
A and B product of B.
B is less than? Say it again.
So A meet B in product of B.
A meet B. Okay, I think you are in the right track here. A meet B is less than B. Okay, so you are, again, you are one step ahead, right? Okay, so okay, why does that help us?
Ότι είναι okay. Άμα έχουμε αυτό, αλλά
You mean I could...
το A και B είναι ένα πράγμα
Okay, you can see what's happening, like in your heart. I can see that in your heart you can see what's happening. Let's make it like more mechanical. There's something missing. You say, okay, this is less than B, and yes, Manolis? B is less than or equal to the other thing. So back to my original question, what are we going to use here, essentially? Exactly, the transitivity of this. But the bad thing is that we need, like, in this point, we need some ingenuity, let's say, someone to think for us. In this case, it was ERRATA, because all the other things I did were pretty much mechanical. Okay, split this like this meet in two, or separate, start here, do that. And then essentially, you reduce everything, and you reach something that this doesn't work anymore, and you say, okay, now it's the time to think a bit. And why do you need like creativity here? It's not, I mean, so much. I don't want to say that what ERRATA said is not useful, but it's not like a very huge inspiration. But the point is that every time you want to reduce this and say, aha, I will use transitivity, I mean, even if I gave you this hint, you would still need the creative step, because there is an infinite amount of things that you can put there. It's not so difficult to see it. So this will be like transitivity of this, because now you need to figure out what is the intermediate thing here. And now if you look at this, it's not so, I mean, you combine it with a hint of Manolis as well, who said, I mean, there is a B in both things, okay. So there should be something here, and the same thing here, right? Okay, and this thing is B, and enough with a hint over analysis maybe. And now I can close both of these. Why? Because for a similar, the dual reason to that, right? Meet is a lower bound of A, and the lower bound of B is below A and below B. So it's below B, because I'm using the right-hand side, and here I'm using, again, the right-hand side of the fact that this is a greater bound of D and B. Okay, does that make sense? Perfect. Okay. So to sum up, I think now you have less excuses to work these exercises. Eventually, okay. Any questions before I continue a little bit still in order theory? Okay. No questions. Okay. So the other thing is the other law that is half. Okay. So this is like always true. But in lattices where you have an actual equality, so you also have the other side, these lattices are called distributive. Okay? So one thing to prove, I don't remember if this is homework or not, I think it is. One thing to prove is that if you have this equality here, you will also have this here. Sorry, the other equality here. And let's talk about this thing, whether you can use like duality or not. Be careful. In Zulip. It's a nice discussion that we can have, or maybe today if we have time. So the other law that it's like always half guaranteed, but not completely, is the modularity. And usually the first time you see modularity, it's not so easy to get an intuition for it. And it helps, I mean, I could write it with weird letters, and it would be like, I'm not sure what's best to do. Start with weird letters and then see it a bit better. I'll start like that. I'll start with the good letters. Or maybe not, okay. Yeah, okay, let's start like that. Here you have that again, the join will end up being less than the mid. But here it's this one. Okay, so this is valid, this whole implication. Be careful, in some lattices we've seen there's something called the exponential object, and sometimes we denote it like that. I should emphasize that this is like an actual implication symbol. Maybe I'll make it longer. And for this reason, I will prefer sometimes to write the exponential object like that, or like that. This is like, in any lattice, if we have this, then we have that, okay? So this is like the safe modularity law. and it's valid in any lattice. And now, if I ask you how to prove it, I don't want to. I mean, you will do that. Okay, you will promise you will do it. You will start with this. Let's say you will put it like in a tree here. You'll keep working your way up, just like we did. See, you have that something is below a meet, right, or something is above a join. A lot of help you can ask, right? And you also have to, eventually, you will need to use that, like A is less than or equal to B. Okay, so again, if you have the full thing means equality. You say that your lattice is a modular one. So this is like so nomenclature and vocabulary. Any questions? No. Okay. It's a theorem that I can never pronounce properly when I try to say it, so I always prefer to draw pictures here. So this is, these are my lattices, let's say, and these are the distributive lattices. And these are the modular lattices. And now I have avoided embarrassment. And the idea is that these inclusions here are and these are the lattices, okay? So there is at least one lattice here and at least one lattice here. So there are lattices that are non-distributive and there are lattices that are non-modular. If you like start drawing lattices, small ones, you will not need to do some very weird construction to find a non-modular one or a non-distributive one. I can draw them here, and we can maybe today, maybe in home, see in fact that they do what they promise. So the idea is that this is non-distributive but modular, and here I will have a blue one that will be like that. So, and these are the smallest ones I can find. So actually, you cannot find it with 4 elements. You need at least 5, but you need 5. 5 is good enough for this counterexample and as well as for this. Okay, this looks very bad. I will draw it again. It's like tap. Let's make it like that. Okay, I mean, you can take it on faith or you can try to break one of the laws. It's definitely the case that you will not break this thing and you will not break this thing because this hold, in fact, in all lattices, so you will break the other thing. You will find something where if you do these operations, it will be not greater than this one. Okay? So, I leave you to check these things. This is not hard at all. It's a very useful theorem, the following. Any lattice that is non-modular, so I'm looking at all these lattices, has a sublattice that is isomorphic to this one. So if you have a lattice and you want to check that to prove that it's non-modular, it's enough to look inside it for like a sublattice for this pattern to appear. If this pattern does not appear, that's an if and only if, right? If this pattern does not appear anywhere as a sublattice, then it's guaranteed that it's modular. And similarly, for this, when you want to check distributivity, now actually you have there are two ways you can guarantee that something is not distributive. Either find this shape inside it as a sublattice, or this one. If you find this one, you say, aha, it's non-distributive, but it's modular, possibly. And if you find this one, you already know that it's neither, okay? So this is quite useful if you have a weird-looking thing. It's easy to spot like sublattices like that or sublattices like that if you want to verify that it's not modular or not distributive. And so the thing that I wanted the last thing I want to say about this, all this like notions is like to try to understand where modularity comes from. I mean, if you look at it like that, the best thing you can say, and actually if I had named these variables like that, renaming on the fly is very bad, and I'm very bad at it, so I will not even try to do it. But let's say it was like that. Okay, so if the right-hand side of the implication was this, what was the left-hand side of the implication? It was A less, do you agree with me? Have I written the same thing just with a correct renaming of the letters or not? I think so, right? It's exactly the same, right? Okay, so if you see it like that, it looks like some kind of associativity, but it's not exactly associativity because the moment you shift the parentheses, the operators flip. Right, you have the join, blah, blah. I mean, it would be associativity, sorry, if you had an equality here, right? So if you had an equality here and you say it like that, and I ask you, like, what is a kind of intuition here? The best you would probably say it's something that's not really intuition, it's just a mnemonic that you remember it, you say, it's just like associativity, but when you do it, you swap joins with meets. And obviously you have the dual thing, I mean, if you are in a modular lattice, which would be like this thing. Okay, so we do have this easy mnemonic thing. It looks like associativity, but it's the moment you do it, you flip joins and meets with joins. But this is not really intuitional. I mean, where does this come from? And to see where this comes from, I need a very simple notion of an interval, which is actually defined in any poset, like a closed interval from A to B. Can somebody guess what this is? The hint I can give you, it's exactly the same definition you've seen when you were in elementary school. I mean, you've seen these definitions, obviously, things like that, right? Intervals. Usually we see them in a totally ordered space, like the real numbers or integers, I don't know. But we don't really need totality to repeat the definition, to copy-paste it. Yes, Stadinos? Okay, he started very well. It's a set, first of all. Okay. Uh-huh. It looks like you're trying to avoid, I mean, you would confuse a child of elementary school. But the child of elementary, we don't need to confuse this child. The child of elementary school knows intervals and knows order. They don't know maybe of joins and meets. They actually know greatest lower common divisor, but they don't know that these are certain joins and meets. But like, I mean, there is no reason to avoid the order. So how can you express this interval? Is all those x's such that? Exactly. Okay, so these are all A is less than X and X is less than B. Okay, this copy-pasted, I haven't generalized it, right? It's exactly copy-pasted. It makes sense in any poset, right? So, but the intervals don't look exactly like, segments. How would they look in general? You would have something like A and B. So it's all those things that, let's try to draw. I want to use the same colors I have here. Let's try to draw everything that's above A. So let's make it like that. Something like that. Okay, let's try to draw everything that's below B. And I will use red for that. Okay. Now, I don't know where to place this thing, but let's say it's somewhere here, maybe. Okay, so what is the interval AB? It's this thing that looks like orange, maybe? Yes. Do you see it? Okay, so this would be the interval, all those things that are above A and below B. Okay, does that make sense? Okay, now imagine that you have an X somewhere in your lattice, and we will reach finally, this idea of modularity. I don't care right now if it's already above A or if it's already below B. So for the general case, I will draw it arbitrarily to satisfy neither of these things. There is a canonical way. Don't ask me what canonical means here, but I hope I can say this word. So there's a canonical way to project X inside the aboves of A, inside the green thing. Can somebody give me like a function, and this is why I say canonical function, that would send X to the green thing? I will give you an example of a non-canonical thing that works, that sends any X to the green thing. Send any X to A. If you send any X to A, you have satisfied the fact that you have mapped X to the green part of the lattice. But it's, you're doing too much, right? If I wanted that, I would just tell you, send everything to A. Send X in a non-abusive way to become guaranteed a green thing. How would you do it, Arete? You're in a lattice, okay?
Θα περιγράφω το σύνολο, το green.
Which,
Το υπόλοιπο σύνολο του πλάτου.
wait, are you talking about this, the outside space? No. Το green, sorry, I heard green. Okay, first of all, what is the green thing? It's, sometimes we call it all the things that are like that, or like that. It's all the x's such that, not x, sorry, all the, I don't know, t's such that a is less than t. Okay? So you mean you would describe this? In what sense? Wait, how do you do that? I mean, I want a nice little function that does this. You send x where? Okay, you're using the wrong operations. I mean, plus and minus, we don't have this thing. We have operations. The idea is to use them. You have joins and meets, Lazarus? Which one? Okay, so just tell me, x gets mapped where? To which element? If you meet, I think you're maybe confusing the word for join and meet, but if you meet x with A, you are definitely under A. The meet is, okay, so it's you join it, right? You need to join with A. So the map I'm using here is like joinness with A. It's this map. You put the argument in the blank, right? So if you do that, you definitely end up somewhere here. I don't like the colors I'm using, but this would be like x join A. Can you see that? Is it? Okay, I think you can see it. Okay. Am I guaranteed to be inside the green part? Yes. Am I guaranteed to be inside the interval? Not necessarily. But I can do something, right? What I can do to make this get inside the interval, there is like pretty much a canonical function that sends everything, maps everything to the best, the least abusive red thing. So what's that? Yes, Arati? Okay, if I started like, okay, but wait, if I just meet x with b, it means that I have forgotten all this work I've done here and I'm back here. Okay, say it. Okay, so the idea is that, wait, you will send this, it's terrible, I mean, okay, sorry for that. So what's the element that you will get here? Okay. When you say or, you mean join? Okay. Wait, this is an order. Or what? X meet B? Yeah, I get what you mean, but I'm not sure why you would do that. I mean, okay. Wait. So the green thing is just, which function is the green one? Let's be done with this here. It's this one, the joining with A. Which function should the red one be? In general, the red one should guarantee it maps things below B. So it should be the meetness with B, right? Okay. So this is like B, sorry again for the terrible colors. So here, what will I reach here? I will reach, I have already realized that I'm doing it in the wrong order, but it works. Yeah, it should be, I will lose. Yeah. Okay, so actually I would like to have the A on the left. That's all I want to change. I know what I'll do. Okay. So I'll swap these things because I want to end up in the formula I have, right? So this should be like this. And now this is like, it doesn't matter technically if you do on the left or on the right because they are commutative, but you will only get the thing I want to get if you do it right. So this is not like that. Let's bring the colors back there. Okay, so now what do I have here? I have A join X, and all this is mated with B, right? So can you guess what we have already shown? So I applied the green function, I'm above A. Now I apply the red function, I'm below B. But what if I do it in the other way around? What if I first want to guarantee that X will be below B and then map it to be above A? I will reach which part? I will reach something like that. So first, let's say it goes here, which is, let's say this element, which I will call, help me here, the red one is the meet with B from the right, this function. So now I am in X meet B. And now I will apply the green one, right? And where should I draw this? So the thing we have proven is this one. I mean, we have not proven it, but you will do it. It's this one, which shows that the join ends up being less than the meet. So the way I have done this is the meet, right? So this thing, if I apply the green one, it will get me here. So how do I describe this element? This is the A meet X join B. Yes, thank you. I knew I would get something wrong. This is the A meet, right? No, the green one meets on the left. So this is A meet, right? The green function is meet with A from the left. So this is A meet. I think I was doing it right.
Wait, I think you need A join parenthesis X meet B, no? Because you already have meet in B.
No, it's weird associativity. It changes join. If you're thinking of the mnemonic rule, I think.
You have meet for B already. Like.
Okay. Yes, you are right. Sorry, this is join. Okay, so the mistake is here. Thank you. So this is joining with A. Yes, it gets me there, and from the left, and the other is meeting B from the right. So yes, so the mistake was there. Thank you. So this is like I will fix it later on. So this is like a join. Right? It's like that. Okay. So this is join. Sorry for that. Yeah. Okay. So this is A join
X meet B.
X meet B, and I think I have missed something somewhere. Yeah, I kept saying that you flip the joins and meets. You don't flip them, right? I mean, you have like join.
Which is within the parentheses, basically.
Yes, okay. So, yeah. So, to sum up, you have two ways, canonical ways, to send something inside the interval. First, guarantee above A, then guarantee below B, and the other one's the other way around. Pretty much modularity says that it doesn't matter if the whole thing commutes. It doesn't matter what you do first. In general, this is not guaranteed. Lattices that have this have some extra nice properties, but at least you know that in any lattice, this will be less than or equal to that. If it's guaranteed that these things coincide, it's a modular lattice. So, okay, last question, then we'll have a break. Say it.
Άρα τι κάνουμε λάθος πριν. Είναι λάθος ο τύπος που γράφαμε για το duality.
No, it's correct. And we found out that it's correct by actually trying to figure it out ourselves. I think at some point I mistakenly said that you swap the parentheses and at the same time you change joins and meets. So this was the mistake. So you don't change joins and meets, right? Okay. But like, let's say you forgot what the mnemonic is, like, thanks to me for making this mistake. You can draw this thing, it will take you like 30 minutes to do it. And then you figure out what the correct thing is.
Άρα είναι κανονικό commutative.
You mean it's not proper associativity because associativity is of a single operation. And now we have two operations. There's no such thing as associativity of two operations at the same time. So this is where it gets a bit fishy. It looks like it because the parenthesis was on the right and you move it on the left, but this is one operation and this is a different operation. Okay, so we stop here. Let's have an 11-minute break. So 12:20 we... Okay, so to change setting, let's go back to categories. And there are like some constructions that I would like to do to show you that we have seen some maybe more complicated, definitely more complicated than these ones, but it kind of seems weird that we skipped these ones. And besides that, I want to start like investigating something. And let's see where this will get us. Since the investigation may take a lot of time, I want to start with this one because it's kind of newer, maybe. Or should I start with the constructions? Okay, I'll start with... Okay, I'll start with the big thing. Let's say I have a sigma thing, okay, what sigma means here. I will denote it by S, and for the time being, I want to leave it open whether this sigma means set or semigroup or monoid. What's next? Somebody? Yes? No, that's before, actually. Yeah, I skipped magma. Okay, let's forget magma. It was before semigroup. So it's set, and I get semigroup. Semigroup means I have a binary operation that's associative. Monoid. No? Yes?
Group.
So the next one is group. Yeah, so monoid, I also have an identity. In group, I have inverses as well. And what's next? After group, it's like... Okay, you know, this is way, it's like a different dimension. So the next thing, I mean, it might be abelian group or whatever. Okay, but let's keep it like that. So I have this S, that it's one of those things. Pick your favorite. And I want to map it. And here, pick your favorite category. And your favorite object inside your category. Let's call it X. So X is an object of some category C, and here I I want to map S not to X, but to, let's say, can someone guess what this means? It's not like the end of X. It's we pronounce it like that sometimes. It's this. Do you remember what we denote by that? It's all the arrows that start from X and stop with the endomorphisms. Endo-arrow. I would prefer to say endo-arrows because it's more agnostic. So it's the endo-arrows of X. So I want to map S to that. And then let's call this rho. And now I want to ask you to figure out what properties this rho should have. Because I don't want it to be arbitrary, I want it to be respectful. And the properties you will pick have to do with, what you have on what this sigma is. If it's a set, rho, I'll try to write it like that. Rho should be a sigma homomorphism. And now it depends on what sigma is, what this means. So if it's a set, what is a homomorphism of sets? What is there to respect in a set? You might be tempted to say nothing. Okay, technically there is something to be respected in any set. Yes? Well, what? Say it again? No, I don't have a set of sets. This S here might be like, a set of persons or whatever. But usually we say that S has no structure. So if you think that a set has no structure, then a homomorphism from a set to another doesn't need to respect anything. Technically, set has a structure. What is it? Yes?
Composition.
Wait, the compositions would be like, if you have an arrow, another arrow, you will compose it. You're thinking, I think, of functors that will respect compositions and identities. What are the homomorphisms between sets? No, wait. Let me rephrase it.
It has to do with the numbers and if you can fit one set into another.
No, but you're thinking of isomorphisms then. What are the arrows in the category of sets? The arrows in the category of groups are group homomorphisms. In the category of monoids, they are monoid homomorphisms. So when we have something that looks like a set, a collection, or whatever, and has some kind of structure, arrows usually end up being things that respect this thing. Lazarus? No? They are functions, yes. So it's associations. I'm trying to look for a different word that doesn't sound like function. It's like rules or mappings or associations that respect... no, ERRATA? Was the same thing? Okay, wait. Okay, you will kill me when I say this, so I'll say it right away. The only structure a set has is...
That when we take a function, each element corresponds only to one.
Pretty much this is the respect what? Equality. Okay, sorry for that, but every set, when you in mathematics, usually when you say set, you assume that it knows how to compare things with equality. You never write it down. But you maybe, I understand the reaction of Manuel here, so you have equality everywhere and whatever. Okay, so, but let's think about what would mean to respect equality. It means that if A is equal to B, then f of A should be equal to f of B. And you say, yes, that's just a function. You can think of an association that doesn't do that. Maybe it maps A to two things or whatever, let's call them associations. So these ones that respect equality, let's give them a name. How do we call them? Functions. So functions technically are homomorphisms of this structure. They respect equalities. Okay? So if you just want to do that, there's nothing extra you need to impose on rho, pretty much. Take your, let's say that S, it's like you guys here, it's like 5, a set of 5 things, and I pick an X in my favorite category. I see all the endomorphisms here. Let's say I have a bunch of them. I can say, okay, that Manolis is this arrow, and RT is that arrow, and Lazarus is that arrow, and maybe I have a bunch of arrows here, and maybe actually Manolis, I don't know, and Sotiris get mapped to the same arrow. Why not? I mean, there's nothing that I'm not breaking equalities. I need to respect equalities, not distinctions. If I wanted to respect this, I would end up with what we call like injective functions. Okay, but I have this, so I can identify things that were not previously identified. Okay, so let's accelerate a bit. What happens if I have a semigroup? If I have a semigroup, it means that this S also has a binary operation. And now if I need to respect it, I need to find a binary operation in these guys here. Remember, these guys are arrows. Okay, do I have a binary operation on these arrows? Yes? Composition. Is it always defined? In this case, yes, because it's from X to X. Okay? So now, if I say that sigma actually was a semigroup, because I like semigroups, I will write the first law that this row needs to satisfy, and it should be what? The row of R operated with S, let's say that R and S are elements of this S, should be equal to, yes?
Row of R composed with row of S.
Do we agree with Manolis? This is what it means, that you respect this operation and you translate it into the other operation. You have that and you're happy, and then you say, okay, what if I like monoids? Where do you still need this one, because monoids you need to respect. A monoid, remember, it has this, and has a unit, and you need to respect all these. Yes, Sotiris?
And you send, you need the identity to send, you don't have an identity, so you have to send the identity. You have, it's a monoid.
Exactly.
The identity goes to the identity.
Okay. You had an inner fight there, an inner struggle, and then, yeah, okay. So this should be, you don't get to say that the identity of the monoid, I will map it anywhere I like. You have to map it on the identity of, from X to X. So this will be, you map it here. Does that make sense? Or I will write it like that. Okay? Makes sense forever? Okay. What if it's a group? What extra you need to respect? If it's a group, you also have inverses here. And yes?
You should map the inverse of something to the inverse of an arrow.
Is there a reason to believe that you have inverses?
Yeah, not necessarily.
Not necessarily. So you say, okay, in case your favorite thing is a group, then you should upgrade or downgrade, depends on how you look at it, to automorphisms from X to X. Remember what the auto arrows are, auto arrows, let's say, are like endo arrows that are invertible. Okay? So they have inverses. So in this case, you say, aha, the extra thing that I have in the group, I have a notion here, and how will I write this? Rho should map this thing to, yes? Rho of R, the inverse of rho of R, right? Where, be careful, the minus one on the left is like the inverse of the group. The minus one on the right is the inverse arrow, okay?
Symbolize it like OP, something like that, or like opposite.
What?
Wasn't the symbolism like OP, something like opposite, in the very early lecture?
No, I don't want to use this. You mean this thing?
Yeah.
No. This thing means literally and only this. It's the corresponding thing in the opposite category. I mean, even if you get something that it doesn't have an inverse, the op means something. It means consider this arrow in the opposite category. So do not confuse. I get why it's confusing. Like, do not confuse this, the inverse of an arrow, if it exists, with the op of it, which is a specific arrow in the opposite category, which always exists. Okay, so we have all this, and Now let's just use a fancy notation for that. And what's this notation that I'm thinking about? It will remind you something, and I will write the same laws. Okay, so instead of saying rho of Rs is something, I will write like that. This thing, should I do it here? Yeah, do it here. No, actually I will not do it here. On the codomain of rho, so which is this one, I only had one thing to worry about, which was like, in this case, something that looks like a monoid, and in this case, something that looks like a group. And I took care of it, and I'm happy, and like everything is done. There are no further conditions imposed by this, since the only thing that I could find extra conditions is in this X here, but I don't even know in which category I am. It's very abstract. Maybe X has no structure, so rho is good. If X had extra stuff that I could maybe worry about, then maybe I would have to say there are extra laws I need, because X has its own stuff, and I need to worry about how rho interacts with X, right? But in this setting I have, there's no extra thing, so there are no extra laws. And now some terminology that you might be familiar with. I think all of you are pretty much, maybe, familiar with this. I have, this is an object of some category C, and rho is from S to, okay, this or X if it happens, or automorphism if it happens to be a group, and this is a sigma homomorphism. And so if I have all these, I call X together with rho. Let's see if anyone has realized how we call this. I'm trying to hide it as much as I can until this point. I think or maybe the mathematicians have seen it, maybe the computer scientists know, but we will see it now. So we call X together with this rho and S, and now this is kind of implicit here, the sigma. I mean, like, pick your favorite sigma. You are very close. Action. I think in the mathematics department, like if you take a group theory or something like that, or representational theory, I don't know, you get to see group actions. You get to see what it means that a group acts on a set. Now, what is the group here? And it's not really a group, because it could be any of these things, and there is no reason to limit myself to groups. If there's a monoid action, or a semi-group action, or a set action, this is the least interesting in a sense, because it's kind of trivial, and it acts on what? I will not say that it acts on a set, I say it acts on an X, where X can be any object of any category. If it happens to be the category of sets, I get the usual thing you've seen, like an action of a group from sets. Technically, this ends up being some functor from groups to set, maybe. Okay, but I want to keep these things like abstract. So if you focus on groups, what you get is the usual definition for an S. You will not call it S, you would call it G if it was a group, so you call it a G set, or a G, and you say that G acts on a set, right? You've seen that? Somebody? No?
I've seen that, not really seen, but I know it exists.
Okay, okay, so I'm trying to make a connection with something you have not seen. Perfect. No worries, because we will end up and we'll read something that I know everyone has seen. Now here comes the tricky part. Like Konstantinos said, the next thing is rings. And I said that's a different dimension. Let's do rings. Okay.
Isn't the group action supposed to end up within the set, whereas here you act, the way the group acts on X,
Yeah.
doesn't give you elements of X.
The what? Sorry. Essentially.
I thought that in group function, you need to end up with elements of x.
And
When a group acts on some set x, you need to end up with elements of x.
we will do that. You will end up in what you mean. I think I understand what you mean. Technically, technically, isn't this something like x? What I have written so far, not what you say, is right? What happens if I carry this? This is already carried. What if I uncarry this? Uncarry this, sorry. Forget my accent, but it's like I have from S to X, and we figured out some laws. Well, if I uncarry this, it will be like, give me something from this to that. And now you see it, okay. And then you would have a different notation probably if you see it like an operation. Usually, if you've seen it in algebra, you've seen it like a dot. You write a dot there or something like that, which is some operation which says you get an element of the group and something of the set, and you give me back a set, right? But where do these weird laws come from? I mean, it's this one. If you translate them, and I'll do it here in a bit, if you translate them in their uncarried way. So it looks like a binary operation now. I don't like the word operation here because you are mixing S's with X's. So it's not an operation, it's a weird thing. It might remind you something because we are used ever since the first semester in mathematics department and in the computer science department, all alike. In the first semester, you are used to having some operations that are like that. That get something of one type and something of a different type, and they give you back something of the second type. Whoever has figured out what I'm saying, keep it to yourself. Okay? I want to follow the lead of Konstantinos here and say, what about rings? Konstantinos likes rings. Let's do rings. What happens with rings? I'm upgrading the sigma to be a ring, and now it looks like I'm in trouble because the ring has how many things? Please give me the correct. There are only two right answers here. How many things does it? I don't mean the carrier set of the ring. I mean the structure of the ring, okay? It's an R together with number of things. Yes?
You need the...
How many? Okay, you're counting? Okay, count.
Okay, you need the identities of two. You need two operations on another two. And you need the inverses for one of the operations. 5.
And that's it. 5 is one of the two correct answers. We'll see the other correct answer in the next class. Okay, so it's like you have the additive part. I will write it like that. Oops, no, that's not additive. And you have the multiplicative part, I will write like that. Probably you will never see it if it's not in a class of mine written in this order, but I like this order, okay? It's first the additive stuff and then the multiplicative stuff. And what are the laws for a ring? Let's remember, this thing is an abelian group, and with these things, it's a monoid. And if I stop there, I would not be doing ring theory, I would be doing some weird kind of simultaneous abelian theory and monoid theory. I definitely need, when I do things like that, I definitely need something that combines the two worlds, and in the case of rings, it's the distributivity, okay? So, rings are like that. So the question is, how do I upgrade, and if I can upgrade my definition of this row here. So again, let's do this. And this is a complaint I have ever since I got like group theory. Okay, let's see what should I copy paste this or not? For starters. Let's forget about this. At least these two, should I copy paste them? Right, I do have the composition, I didn't lose anything. The problem is that I have extra structure. I'll just emphasize my point. Let's say that this is a ring, okay? It's an R, okay? So I have an extra thing, and I'm looking for an extra thing there. And I will not find it if I'm in an arbitrary category that I know nothing about. But there is something that you may have seen, and this is my frustration here, because the first time you study like abstract algebra, and you study groups, there is a perfect canonical example of the perfect guide to guide you through group theory. What is the perfect group?
ZM.
That's no. You said ZM. Why is it not so perfect? It's too good. Okay. Yeah, what's the first example you see from a group? Usually it's not like that. Maybe it is, but you definitely meet.
Symmetry group.
Yes. Okay. So why is it a better thing? For example, it's not commutative, right? You want to study groups. You don't have any obligation to be commutative. Your guide, your default example, your guiding example should be like that. What is the default example for rings? I think I never saw that while studying algebra here. I mean, probably you see it somewhere, but it's never like the symmetry Sn. You mean like for any n's? What?
The integer.
We've seen that they have a nice property in the world of rings. Nobody continued this. It was an exercise to prove that it's an initial object in the category of rings. It's not so good. First of all, it's commutative. I mean, if you think of commutative rings, I'll give you a maybe. But for the same reason that you don't get the real numbers with addition for groups, why would you get something that's commutative if you want to study not necessarily commutative rings? So a good... Okay, you're thinking like, what is not commutative? That's very cool. Okay, so the default example here is what happens if you have this thing. If you look at the endomorphisms of an abelian group A, this is abelian. And I will leave it as an exercise because this is like the math part to show that this actually forms a ring. But we need to discuss at least what are the operations here, because first of all, I already have something that looks like multiplication, which is composition, and it has an identity, which should have an identity because I'm in a ring and not a rung. So I know what the multiplicative part is. This will be composition, this will be the identities. Okay, what about these things? Obviously, these things have to come from the fact that within this A, which is an abelian group, I have an operation, and somewhere you will probably need this commutativity thing. So anybody has an idea of how to define an addition for those things. Remember, these things are maps from an abelian group to an abelian group, which means they are group homomorphisms. It's these things, right? This is X here. My elements are these arrows. I already know that I can multiply them, composition. I already know which is the identity of multiplication. It's the identity of homomorphism. What does it mean to sum them? Like if I have, let's give them a name here. I have phi and I have psi. Okay, what would be phi plus psi? First of all, what kind of thing is this? What kind of thing should it be? Yes? And the endomorphisms, I changed my letter. Sorry, this was A. An endomorphism from the abelian group A to itself. So yes, so let's try to define it. I need to say where it maps the little x of A. And I hope you can see that there is only one obvious way to do that. I need to produce an element of A, and I have an element of A. Okay, please don't say X, because this is technically, it type checks, okay, but it's not obviously what we want. Manolis?
Phi of X star or star of
Let's use plus. People that do abelian groups like the additive notation. So I hope it's kind of obvious that this is the new addition I'm defining on the ring, while this one is like the addition I already have in the abelian group A. If you try to, what do I need to prove? Yes?
First of all, that it is indeed homomorphism.
Yes. No. And in it, surprisingly, you will need the commutativity. Okay, so do that. If you do it without the commutativity, probably you have cheated somewhere. Okay, so indeed, when this thing is an abelian group, I have some extra structure here. It is a ring. And on the other hand, I had a ring, so I already know what it means to be a ring homomorphism. What are the extra stuff I need to write? Somebody help me. About the multiplicative part is what I had already, but I need also somebody. Yes?
It's to preserve addition.
Just to emphasize and get you used to this. Okay. What else? 0 should be mapped to. What is the 0 of this ring? Yeah, within my yes?
Function that sends everything to
Exactly. So this 0 thing, when you map it to x, this should send it to the 0 of the identity of the abelian group, right? Okay, this should be the 0. What else? There's something else in rings. The minus r should be mapped to the, what do we have here? The minus rho of r. And here I will need to worry now about what it means, what is the minus phi of x, which is kind of obvious.
I'm sorry.
Yes.
Can you explain what is 0 of the abelian group? Is it the same?
The identity of the abelian group.
And then what do you do with the 1? What do you do?
There is no, in the abelian group, there's no such thing as 1.
I mean, you are in a ring, right? And you
So, okay, let's see.
have both the unit and the 0.
So technically, I'm here. The endomorphisms of, this is my set, and the operations are this weird x, this weird plus that I have here, this 0, that's this thing, the minus thing that I'm defining here, this is the additive part of my ring, and then I also have the identity homomorphism, let's call it, I don't know, something like that, and what else? The composition. Does that make sense?
I don't understand what the 0 in this context is.
Wait, is it this 0 or that 0?
The 0A.
The 0A? Okay, A is an abelian group.
Yes.
It has an identity since it's a group.
Isn't this 1A?
No, it's called 0. I mean, I'm using additive notation for the abelian groups. So the identity element of this group, I call it 0, and the multiplication, I'm calling it plus. The operation, I'm calling it plus, and the inverses, I'm calling them minus. It's quite common when you do abelian groups to use additive notation. People will kill you if you do the other way around, if you use plus without knowing that it's commutative. And the multiplicative part, forget what happens inside the group. The multiplicative part has to do with these arrows. But what I'm trying to do is like shift the operations that I have inside this thing, plus 0 and minus, to operate here as well. So I have brought these things up to the same level of arrows, and now having the same carrier set, plus minus 0 times and 1. So it's a ring. So, and it needs to satisfy these things, right? And we're getting close to the aha moment, because so far I have just said that this is a ring, right? Yes?
I don't think it really matters, but shouldn't minus 5x be minus the 5x? Shouldn't the minus be on the outside?
Yep, completely. You're absolutely right. What I wrote didn't make sense. This is the minus. Thank you. This is the minus of the abelian group, and I'm applying this thing to the phi of x. Like call phi on x. You are inside the abelian group, and now take the inverse inside the abelian group. This makes sense. Okay, thank you.
I think it would be the same anyway because it's doesn't follows the morphism, so it should be
Even if it ends up being the same, I mean, this is the thing I want to write. Technically, is this one? Yeah. So this is the correct thing. The other, I will not accept the other thing as the correct thing. Okay. So, am I done? We still have 5 minutes, so I'm not done. But I mean, the subject is not done yet. Why? There's some extra things that I need to worry about. What are these extra things I need to worry about? By the end of this lecture, you will either say you have seen the best or the worst definition of something. I'm curious. Okay. So far, I hope you're with me in the sense that we haven't done any arbitrary choices of what laws I'm writing down. It's the obvious things. I have a ring here, it's a ring there, it should be a ring homomorphism. Okay. But now pick your favorite R inside R. What is rho of R? What kind of thing is it? Where does it live? Yes, yes? No, you are right. So rho of R, it's an element of the blah blah. So how do we call them? So in particular, I'm trying to get to the idea that it's a group homomorphism. Since it's one of these arrows, it's a group homomorphism. But I haven't read, so let's write these rules down. These rules down. What does it mean that it's a group homomorphism? It has to be to respect some things, right? So what does that mean? Associative, no, what? Sorry? It's a group homomorphism, right? It respects three things, all right? Okay, so eventually I want to write this down with a notation that will be similar to what help me here, what Sotiris was saying about I'm carrying this thing and that it looks a bit weird the way I'm writing it. So let's do this thing first and come back down there. So if I carry this, I need something that takes an element of rho. You could give me something like what's the best way to note this? Okay, I'm kind of pressed by time here. I have 2 minutes. I will need like 4. Bear with me. If I see it, it's like that initially, right? It's like this. And I can say the rho of S does that, maps this element of S to this endomorphism, whatever. I want to see it like a binary thing that has this form. And let's denote it invisibly, juxtaposition. So the idea here would be that I have this, and I will translate these 3 laws here, and you will see where I'm going with this. So the first one would be RS multiplied or whatever, how you want to call it, with some, let's call it A. This should be what am I doing here? Which letters? They are. I'm using R, little r and s, little s as elements of this s here. And I'm trying to translate what this law, like that. Because this pretty much tells you if this thing is equal to that thing, it means like if you apply to an A, you should have this equality. Right? I have completely lost you, and I think I cannot regain you back in like 0 minutes. Okay, so I think it's a good time to stop here.
The next episode.
What?
At the next episode.
Can somebody guess what's here? Okay, so I want to do this properly, so let's do it on Friday. We'll end up, so I will not find out if you think this is the best or the worst definition of something. By the fact that we didn't complete it in this lecture, maybe it's the worst. But I hope that by the next lecture it will become maybe the best. So, see you like on Friday. Do the homework.